Hi everyone, we're going to be talking about derivatives today. Now, before we actually take a look at our notes, first I want to talk about something that you already know. Right, so first let's talk about slope. All right, you could list several things that you know about slope, I'm sure, but the biggest idea that you learned from Algebra 1 is that slope is rise over run. Right, and another way of saying the exact same thing is it is the change in y over the change in x. Or a shortcut math way of saying that is delta y over delta x, where that triangle is just the Greek letter delta, and it just refers to change. All right, and specifically what I mean by change is if we draw a graph, and say we have some function, right? And if I pick 2 points on this function, I want to figure out what's going on between those. Well, this is going to have some x value, and this is also going to have some x value, so we'll call that x2. And we have some y value and some second y value. Well, there's a literal distance between these x values, and there's a literal distance between these y values, and you can just subtract them, and you'll get your delta y and your delta x. That's literally what we're doing here. Now, something else that you can do with this graph is you can draw a line connecting these 2 points. So if I draw a line that connects these 2 points, I have what's called a secant line. And my secant just intersects my graph through 2 points. And what my secant tells me is the average rate of change. Right? Sometimes we call that AROC. Yeah, that's my average rate of change. So for instance, if, I don't know, like on my x-axis, this is time, and this is, I don't know, say distance or something like that. Then over this amount of time, I traveled this much distance. So in this span of time, my distance changed by this much, and that's my average rate of change. Okay, so something like miles per hour would be your unit or something like that. Okay, now what if we wanted to get more specific and instead of over a period of time, we wanted something at one instant in time? Okay, so what we call the instantaneous rate of change. All right, well, initially we run into some problems. So say I go to my graph again. Okay, well, if I pick a point, there's not much I can do with that in terms of a secant. Obviously, if I pick a point here and I try to calculate the slope using only that point, I'm going to end up with the same thing on top and bottom. All right, so I'm going to end up subtracting similar quantities. I'm going to get 0 over 0. Nothing good's going to happen. We're sad. So let's take a look at this picture here. All right, so here I have a function and I have a secant line. This green line is my secant line, okay? And as I bring my points closer and closer together, I see that it approaches what we call that tangent line. So as I bring these closer and closer together, I can still get some sort of information out of this. Okay, it's not a secant quite, I mean, it's a tangent, but in essence, we can still think about using 2 points. And that's where the idea of a limit comes into play, right? So I have these 2 points, and I'm thinking about my delta x, right? So at this point, my delta x is maybe 1. And as I keep going, I bring my delta x closer together. Now my delta x is maybe 5, right? And as I keep bringing it closer together, it's getting closer and closer and closer until I actually hit something, right? And this is where the definition of a derivative in your notes comes from. So we have a limit definition of a derivative here in your notes, And I'm going to tell you that this is basically just slope. Okay, this is nothing fancy. It's just slope. Now, again, the reason why we have to use a limit is because we're bringing these 2 points that we're picking really, 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 really close together, like infinitesimally close together. So my x1 and my x2 are even closer together than that. They're really, really close together. That's what that limit is doing. So I'm going to give you a different looking definition. This is one that you'll see. In your book, they use h, but this is the exact same thing. So I have the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x, where delta x is just the distance between my 2 points. Now this is just slope. So let's draw a graph with a nice curve. All right, and let's define some points here. All right. So if I say that this is x, say, then I can say that this is x plus delta x because my distance is delta x, right? Similar thing here. Because this is x, I can say that this is f of x. It's like the fancy version of saying y. So it's x, the corresponding coordinate is going to be y or f of x. And same thing here, this is just f of x plus delta x. All right, and notice what happened here. We subtracted our y values, so I subtracted my y values on top, and I subtracted my x values on bottom, and these x's canceled, and that's why I just have a delta x there. And again, the reason why we have a limit is because I'm bringing these points really, really close together. My delta x, my distance between my points, is approaching 0. And that leaves me with what we call a tangent line, and that is my derivative. And that's what we call the instantaneous rate of change. So now I can calculate how fast you're going, say, at 1 instant in time, not just over a period of time. All right, you're also given an alternative form, and we'll talk about that a little later. But first, let's look at our first example. So we're given that a diver jumps into some water, and we have a function. This is a very common function, so get used to it. And first, we want to graph this. So I know that I start at 32 and I go in a downwards parabola because we're jumping in water. So this is time and this is feet above the water, distance, whatever you want to call it. Okay, now they ask us to find the average velocity or the average rate of change at which the diver is moving between 1 and 1.5 seconds. Right, so these are my x values, so I have to find my y values. Right, so notice they call our function s. So my y values are going to be s at 1.5 minus s at 1 divided by 1.5 minus 1. Right, now you just plug these into your function. You could do that in your calculator. You would get 20 minus 32 over 0.5. Right, and as a final answer, you would get negative 24 feet per second. Right, we got to keep our units. Now you might wonder why it's negative. Well, look at the direction that we're going. We're going down. Right, so our velocity would need to reflect that. So it would definitely need to be negative. So I know I did a good job. All right. Now we need to compute the average velocity over these specific time intervals. These are very small time intervals. So this is very similar to the limit tables that we did earlier. So I'm just going to write down what I got. All right, you can check me. Try to catch a mistake. So between this, I got negative 14.4, negative 15.84, negative 15.98, negative 17.6, negative 16.16, negative 16.016. And the question is, what are we approaching? So as I go to smaller and smaller intervals, so notice how the distance in my interval between my first and second point is getting smaller. It looks like I'm approaching negative 16. And same thing here. As I go to the right, as my distance between these two intervals gets smaller and smaller, looks like I'm approaching negative 16. So that's what I'm going to go with, negative 16 feet per second. And that's about it. I will see you all later.